Hello there, and welcome to Just About Earth, where curiosity gets cozy and science takes the scenic route to slumber. Tonight, we drift into a question as ancient as the oceans and as vast as the sky. Yet one you might never have thought to ask. A question hiding in plain sight, lapping at our shores and swirling in our teacups. Where did all the water on Earth come from? It's a funny thing, isn't it? Our planet, this pale blue dot, is awash with water, oceans that cradle continents, clouds that whisper across the sky, and rivers that braid the land like silver thread. It's so ordinary that we forget how extraordinary it really is. The seas feel eternal, but they had a beginning. And that beginning, well, it might be older, colder, and stranger than you think. So before we dive into cosmic clouds and ancient stones, let me ask, what time is it where you are? Is it morning coffee, a quiet afternoon, or the hush of midnight rain? If you find this journey soothing, if it brings wonder to your window, I'd be ever so grateful if you liked the video, subscribed, or shared it with someone else floating through time and curiosity. So settle in, slow your thoughts, and let's begin. Because in the story of Earth, water is both the ink and the paper. And to find its source, we must sail beyond the sky, across time itself, to a moment before there was even a sea to remember. Roughly 4.6 billion years ago, Earth was born not as a gentle blue marble, but as a fireball, dry, molten, and merciless. And yet today, over 70% of its surface is covered in water. Liquid water, a delicate, rare, life-giving phenomenon. But how did it get here? Was it always part of Earth's makeup, lurking in its molten heart? Or did it come from somewhere else, delivered perhaps by icy messengers from the depths of space? Tonight, we follow the water's story, from interstellar ice to deep mantle secrets, from violent impacts to gentle rains. Because to understand where Earth's water came from, we need to go back, way back. Back before oceans, before rivers, before Earth even had a surface. Back to the beginning. In the quiet vaults beneath Honolulu, inside a building that could pass for just another university annex, a tiny fragment of Earth's deep memory once set, off a cascade of questions that reached all the way to the stars. The year was 2014, and a team of geochemists led by Dr. Lydia Halis was studying microscopic inclusions within an ancient basalt rock, a relic from the early mantle of Earth, brought to the surface by volcanic forces. These inclusions, mere specks of glass trapped in the mineral olivine, carried within them isotopic fingerprints, clues, whispers from a pre-existing Earth, time when Earth was still forming. And inside those clues, they found something strange. Deuterium, heavy hydrogen. The ratio of deuterium to hydrogen, or DH, is a kind of cosmic signature. Different sources of water in the universe have different ratios, and what her team found was this. The DH ratio in those mantle samples was much lower than that found in our oceans today, much lower than the signature carried by comets. In fact, it closely matched the DH ratios found in certain types of meteorites, particularly carbonaceous chondrites, primitive ancient space rocks. This tiny chemical difference cracked open a window to the past and poured starlight through, because in that moment, they realized something extraordinary. Earth's water may not have come from comets as long assumed. It might have come from something even older, from the very building blocks of the planet itself. But to make sense of that, we must first understand how Earth formed, not as a quiet miracle, but as a storm of stone. The solar system was born in chaos, a rotating disk of gas and dust surrounded the young sun, hot, turbulent, and glowing. Within this disk, grains of dust began to stick together, then clump, then collide. Over millions of years, they formed larger and larger bodies, planetmouths, protoplanets, a cosmic demolition derby, where gravity was both the hammer and the glue. Our Earth began as one of these protoplanets, a growing ball of rock and metal smashed together from countless smaller pieces. And some of those pieces carried water, but not the way we see water now. Not oceans or rainstorms. This was water trapped in minerals, bound tightly within the crystal structures of silicate hidden in dust. Hydrated. Minerals formed in the cold outer regions of the solar nebula, far from the sun's warmth. They journeyed inward, carried by migrating asteroids and gravitational nudges. When they collided with Earth, they released their ancient moisture not in drops, but in bursts of steam. And that's the paradox. Earth began hot, really hot, hot enough to vaporize anything wet. The surface was molten. The atmosphere, if you could call it that, was more of a temporary blanket of rock vapor. So, how did any water survive? Some didn't. Much of the water delivered early on was likely lost, boiled off into space by solar wind, or blasted away by impacts. But not all of it. Deep beneath the surface, some water found refuge, locked into minerals, sinking slowly into Earth's forming mantle. And when the magma oceans cooled and the crust began to form, volcanic outgassing began. Steam, hydrogen, oxygen, carbon dioxide, and among them, water vapor. Rain fell for the first time. Not a gentle drizzle, but torrential storms that lasted for thousands of years. Rain that turned fire into ocean. But here's the twist. If Earth's water came from these ancient water-bearing planetimals, these chondrites, then Earth was always destined to be wet. Maybe not blue at first, but damp deep down. Which raises a beautiful possibility. The ingredients for oceans were baked into the recipe from the start. Still, the picture isn't complete, because there's another piece of the puzzle. Those icy comets that blaze across our skies like whispers from the outer dark. For decades, comets were the prime suspects in the mystery of Earth's water. After all, they're made largely of ice. What could be more intuitive? Icy visitors from the Kuiper Belt, or the distant Oort cloud slamming into the early Earth and melting into seas. And indeed, early in Earth's history, impacts were frequent, violent, planet-shaping. The late heavy bombardment around 4 billion years ago was a time of relentless cosmic rain, not of water, but of rock and ice. If comets were responsible for Earth's water, that would have been their moment. But as we've seen when we actually measured their isotopic fingerprints, their DH ratios, something didn't match. Most comets have too much deuterium. Their water isn't the same as Earth's. It's close, but not quite. Like finding a green spandex puzzle piece that nearly fits, but won't click. Some comets, especially those from the asteroid belt rather than the distant outer solar system, have DH ratios closer to Earth's. But even then, the match isn't perfect. And the amount of water they could have delivered, it's not enough. So perhaps comets played a minor role. A drizzle rather than a flood. It's the carbonaceous chondrites, those ancient meteorites, that now seem to carry the best match. They formed in the early solar system. They wandered. They collided. And in doing so, they became the couriers of Earth's oceans. And yet, this story, rich with isotopes and orbital mechanics, still leaves room for wonder. Because even if the water came from space rocks, the moment it rained down upon this world, it transformed everything. Imagine it. A red-hot Earth, crust cracking with magma, sky thick with steam. Then, the first true storm. Not lightning, just rain. Sheets of it, falling for centuries. Sculpting the first rivers, filling the first basins, birthing the first sea. Water born of stone and fire, draping the planet in life's future promise. So the next time you dip your fingers into the sea, remember you're touching a molecule that once rode through space, bound to a pebble older than Earth. It crossed billions of miles. It endured impact, fire, and pressure. And it remained, ready to become part of an ocean. A cloud, a tear, a breath. Water didn't just come to Earth. It stayed. Before the seas churned, before clouds even had the breath to form, Earth was a smoldering, spinning question mark, suspended in the newborn solar system. Picture it, not the lush blue marble we know, but a tempest of stone and heat, a molten sphere glowing faintly red like the eye of a forgotten forge. Its surface wasn't solid, not yet. It was a restless ocean of lava, constantly stirred by impacts, constantly reshaped by the chaos of its own infancy. This was Earth in its first few million years, and in this version of the planet, water, if it existed at all, was not something you could drink or swim in. It was a ghost, a vapor, a chemical whisper, bound inside rocks, or drifting like steam through an atmosphere thick with sulfur, carbon dioxide, and silicate. Back then, the atmosphere was not the gentle envelope of blue we breathe today. It was choking and dense, more a plume than a sky. Volcanic outgassing pumped it full of greenhouse gases, while the sun, fainter than it is now, cast pale light across a world that still had no oceans to catch it. There were no continents, no stable crusts. Land where it existed was fleeting, hardened temporarily by cooling, but often broken again by new flows of magma. And in this shifting seascape of fire, deep beneath the forming crust, minerals were beginning to capture hydrogen and oxygen, the raw ingredients of water, holding them in silicate cages that would eventually be unlocked by heat and pressure. This early world was governed by processes we barely experience today. Giant impacts were common. Some were so massive they could melt entire hemispheres. One, perhaps the most famous, is thought to have formed the moon itself. A Mars-sized body named Theia collided with the proto-Earth, ejecting enough debris to form a satellite and reshaping our young planet forever. And yet, these cataclysms were not the end. They were the beginning. Each impact, each fracture in the crust, offered new paths for internal gases to escape. Hydrogen, carbon monoxide, water vapor. As the planet cooled, these gases condensed. What once boiled skyward began to fall. The first rains, acidic, yes, an alien, began their descent. Imagine the sound, not a pitter-patter, but a constant hiss. Rains striking magma, exploding into steam. Rivers couldn't form yet. There was no land stable enough to carve. Instead, pools of water boiled away as quickly as they appeared. But slowly, steadily, the surface began to change. Cooling took time, hundreds of millions of years. But eventually, magma oceans gave way to a solid crust, thin and precarious though it was. It cracked and buckled under its own heat, releasing more gas, more steam, and more opportunity for water to linger. This was the Hadean Aeon, named for Hades, the underworld. A fitting title for a place of such fury and fire. But even in this inferno, life's eventual requirements were quietly assembling. And here we must pause, because to talk about water on Earth, without speaking of Earth's interior, is to skip the heart of the story. Beneath your feet, miles down, far below the crust, lies a region called the mantle. Solid, but hot enough to flow over time. It's in this mantle that Earth stores its ancient secrets. And astonishingly, we now believe that the mantle holds as much water as, or perhaps even more than, all the oceans combined. Not in lakes or underground rivers, but locked inside minerals like ringwoodite and wadzite, crystals capable of trapping water within their structure, holding it under pressures far beyond anything found at the surface. This water isn't accessible. It doesn't slosh or drip, but it's real, and it tells us something remarkable. Earth didn't just acquire water from the outside. It may have grown up wet from the inside out, because those planetimals, the chondrites, and early space rocks brought not just water to the surface, but to the core, to the very bones of the planet. And some of that water never left. The implications are staggering. It means water wasn't a latecomer. It was foundational, present during differentiation, when Earth's layers formed, present during the moon-forming impact, present perhaps when the first seas finally gathered into basins that were cool enough to hold them. Let's turn to those seas. Once the surface cooled enough to remain solid, and the atmosphere had thickened with enough vapor, Earth's first true oceans began to appear. Not all at once. There was no sudden moment when someone could have looked out and seen a gleaming blue expanse. But over time, puddles became lakes. Lakes joined into seas, and eventually the oceans formed, shallow by modern standards, and constantly reshaped by volcanism, meteor strikes, and tectonic rumblings. The skies above them were not yet blue. With no free oxygen, the atmosphere was a hazy soup of methane, ammonia, and carbon dioxide. The sun's ultraviolet rays pierced it easily, and without an ozone layer, radiation bathed the surface. And yet, despite all this, the oceans endured, held in place not by gravity alone, but by Earth's unique balance of heat, pressure, and atmospheric conditions. It was a delicate recipe, just a little closer to the sun, and water might never have condensed. A little farther, and it might have frozen forever. But here, in this golden range known as the habitable zone, it lingered. Still, these early oceans were nothing like what we know. They were acidic, greenish, perhaps from dissolved iron, warm, stirred by constant geothermal activity from below. Hydrothermal vents, underwater geysers, fed by volcanic heat, spewed minerals and heat into the depths, forming environments that many scientists now believe could have been the cradle of life. No coral reefs, no fish, just water, rock, heat, and time. And perhaps something else. Organic molecules, drifting in from space, or forming in the broth of early Earth. Amino acids, simple sugars, the seeds of biology. In these ancient waters, chemistry had room to stretch out, to experiment, to combine and recombine, and perhaps quietly, slowly, to awaken. Because before Earth became a home, before it was lush and green and full of voices, it was simply wet. A planet of storms, seas, and silence. And in that silence, something stirred. To understand the true source of Earth's water, not just how it arrived, but how it took root, stayed, and reshaped the very nature of our planet. The planet, we must follow a trail written not in oceans, but in isotopes. It begins with hydrogen, the most abundant element in the universe. Light, ancient, forged in the earliest moments after the Big Bang. But hydrogen is not uniform. Some of its atoms carry an extra neutron, a variant called deuterium. It's still hydrogen, just heavier. The ratio between regular hydrogen and deuterium acts like a cosmic passport stamp. It tells us where a given sample of water has been, whether it condensed in the outer reaches of the solar system, formed on a cold asteroid, or emerged from volcanic gas. This is the deuterium to hydrogen ratio, DH. Earth's seawater has a specific DH ratio. For decades, scientists compared it to known sources: icy comets, asteroids, meteorites, and even the solar wind. The results weren't just data points, they were fingerprints, and they pointed to something strange. Let's begin with comets. Comets, those icy nomads from the solar system's fringes, seem like perfect water couriers. But most of the ones we've studied, like Comet Halley or Hale-Bopp, have dished ratios significantly higher than Earth's. If Earth's oceans came from these icy wanderers, they would be chemically different. They are not. Some comets from the Kuiper Belt do have ratios closer to Earth's, but they're the exception, not the rule. And even if all of them struck Earth, they wouldn't have delivered enough water to fill our oceans. It's a lovely idea, oceans as cometary gifts. But the math and the chemistry say otherwise. That brings us to meteorites, specifically a rare group called carbonaceous chondrites. These are among the oldest solid objects in the solar system, tiny time capsules that formed in the dusty midplane of the solar nebula over 4.5 billion years ago. Some of them never underwent the melting and differentiation that reshaped larger bodies. As such, they preserve ancient chemistry, including water. When researchers began studying their deuterium to hydrogen ratios, a pattern emerged. They matched Earth's oceans, not just closely, almost perfectly. These meteorites contain hydrated minerals, evidence that water wasn't just carried, but locked inside their very structure. And their isotopic fingerprints suggest they formed in a part of the solar system not far from where Earth assembled the inner asteroid belt. Suddenly, a picture started to form. Earth didn't wait for comets to bring water. It inherited it. Not as ice, but as hydrated rock. A delivery not in buckets, but in billions of tiny grains. The process likely began during accretion. As the planet grew, it gobbled up rocky material, some dry, some wet. The wet bits contained silicates, rich in O bonds, essentially water-bound into minerals. These were not surface waters. They were deep, trapped in the forming mantle. And when the planet differentiated, when heavy elements like iron sank inward to form the core, and lighter silicates rose to make the mantle, those hydrated minerals were carried along. But here's the key. This wasn't just storage. It was transformation. Over time, as internal heat built and volcanic activity increased, these bound waters were released. The Earth began to outgas not only nitrogen, but water vapor. Plumes of steam rising from fissures flowing from mid-ocean ridges. The planet exhaled, and the atmosphere, thick and volatile, became saturated. Eventually, when the surface cooled enough, the water condensed. The rains began, and they did not stop. It was not a single storm. It was an epic of deluge, a hydrological era where clouds formed endlessly and rain pounded the surface like a baptism. Pools merged into seas, basins filled, water collected in lowlands, carving paths, shaping valleys, even as the crust itself still shifted beneath. But there's another theory, one even older, colder, and stranger. Some scientists propose that Earth's water began arriving before the planet itself was fully formed. The very dust from which it grew. In the frigid reaches of the solar nebula, well beyond the young sun's warmth, ices formed not just of water, but of carbon monoxide, methane, ammonia. These ices coated grains of silicate dust, the raw material of planets. As turbulence and gravity stirred the disk, some of these icy grains drifted inward. They didn't melt right away. They stuck to growing clumps. They added their mass to planet decimals, and they brought their water with them. In this model, Earth's wetness is not an add-on. It's primordial. The planet didn't become wet. It was born wet, at least in parts. This might explain something curious: the consistency of water's isotopic signature across the planet. From deep mantle rocks to surface oceans, from ice caps to underground aquifers, the DH ratio remains remarkably stable. That kind of uniformity suggests a shared origin, not a patchwork of deliveries, but a foundational source. But there's still the question of retention. Even if water arrived early, how did it stay? The early Earth was hot, very hot, enough to boil water instantly, enough to strip light gases from the atmosphere. Some researchers believe Earth's first oceans may have formed and then vanished, lost to space by solar wind or massive impacts. So why didn't all the water escape? Two reasons. First, Earth is big. Its gravity is strong enough to hold on to heavier molecules like water vapor, even during violent periods. Second, by the time water was abundant at the surface, Earth had begun to form a magnetosphere, a protective magnetic shield generated by the spinning of its molten iron core. This shield deflected the solar wind, preserving the atmosphere and the water within it. Without this magnetosphere, Earth might have suffered the fate of Mars, a planet that once had water but lost much of it to space. So the real miracle isn't just that Earth received water. It's that it held on, that it kept raining long enough, that it cooled quickly enough, and that it protected itself fiercely enough to cradle the oceans we know today. Water came early. It came often, but most of all, it stayed. And in that act of staying, everything changed. Let's return now to the Earth, not as a molten sphere or a newly crusted orb, but as a world at a threshold, a place just beginning to wear its oceans like a loose-fitting robe. Something profound was shifting, not in a single moment, but across millions of years, as water moved from a vaporized dream into a planetary feature. The transformation was not subtle. It involved the entire planet's geochemistry, the cycles of heat and pressure that dictated whether water remained locked in minerals or burst free in steam. This is where Earth's deep mantle re-enters the story, not as a background detail, but as a central player. You see, the water cycle we know, the endless rise and fall of evaporation, condensation, precipitation, isn't just a surface phenomenon. There's another cycle beneath our feet, one that may be just as old and just as vital. The deep water cycle. It works like this. As tectonic plates move, grinding, sinking, colliding, some are forced downward into the mantle in a process called subduction. And with them, they drag seawater, not as liquid, but bound within hydrated minerals like serpentine. This water travels deep, sometimes hundreds of kilometers down, where pressures and temperatures squeeze and bake it into new forms. Some of it stays trapped, but much of it eventually comes back, released from the rock by heat, rising through magma and erupting in volcanoes or mid-ocean ridges as steam. Over time, this cycle becomes a planetary heartbeat. Water in, water out. Not fast, not dramatic, but steady and vital. It's this internal breathing of the Earth that may have allowed the oceans to reach a stable volume. Without it, water might have endlessly accumulated or vanished altogether. But with it, the oceans became sustainable. A layer, not a flood. Still, there was another trigger, one that helped transform oceans from chemical basins into biological incubators. It was oxygen. Not the oxygen we breathe today, not yet, but its slow, subtle introduction was linked to life itself. Around 3.8 billion years ago, as the earliest oceans settled, something extraordinary began. The first signs of life. Microbes. Simple, ancient, astonishing. They didn't need oxygen to survive. In fact, they would have found it toxic. Instead, they thrived on chemistry, using heat from hydrothermal vents or sunlight filtered through a haze-filled sky to power their primitive metabolisms. Among these early life forms were cyanobacteria, tiny architects of planetary change. They lived in shallow waters, clustering in mats or domes known as stromatolites, and they did something no creature had done before. They performed photosynthesis. They used sunlight to convert carbon dioxide and water into energy, and in the process released oxygen as a byproduct. At first, that oxygen didn't linger. It bonded with iron in the oceans, forming rust-cold bands of rock that we still find today. Banded iron formations, geological evidence of Earth's slow oxidation. But eventually, the oxygen began to accumulate, first in the oceans, then in the air. The beginning, what scientists call the Great Oxidation Event, around 2.4 billion years ago. It wasn't fast. It wasn't even uniform. But it reshaped the planet's chemistry and the water along with it. Oceans became less acidic. New minerals formed. Biological complexity increased. Life adapted. Some perished, others evolved. And the atmosphere began its slow transformation toward the breathable blend we know today. All of this hinged on water. Water carried the carbon. Water housed the microbes. Water stabilized the climate, buffered the temperatures, and enabled reactions that would be impossible in a dry world. Yet, water was not just a passive medium. It shaped the very skin of the Earth. Over time, it carved valleys, wore down mountains, and created the sediments that would become soil. It formed rivers that rearranged continents. It became glaciers that ground rock into dust and reshaped entire landscapes. But even more than that, water regulated the thermostat. Thanks to its high heat capacity, water can absorb large amounts of heat without changing temperature. This helped Earth avoid the wild swings of climate that plague other planets. It allowed for moderation, for consistency, for habitability. And beyond this, water enabled the formation of the carbonate-silicate cycle, a long-term feedback loop where carbon dioxide is drawn out of the atmosphere by weathering, stored in rocks, and eventually returned by volcanic activity. Without this balance, Earth might have become a runaway greenhouse like Venus or a frozen snowball like Mars. Instead, it stayed temperate, stable, wet. There's also the question of Earth's unique hydrosphere compared to its rocky neighbors. Venus and Mars may have once had water, possibly even oceans, but neither retained them. Venus, close to the Sun, experienced a runaway greenhouse effect. Water boiled off and was broken apart by solar radiation. The hydrogen escaped, the oxygen bonded with rock, and the planet was left bone dry under a crushing atmosphere of carbon dioxide. Mars, smaller and farther out, lost its internal heat more quickly. Its magnetic field faded. Without protection, solar winds stripped away the atmosphere. Any water that remained either froze or seeped underground. The rivers dried. The seas vanished. Only Earth held on, because of its mass, its magnetic field, its distance from the Sun, its internal cycles, and yes, its luck. It was in many ways a perfect storm, and water was both the cause and the effect. From stardust to storm clouds, from minerals to monsoons, water's journey wasn't just a delivery. It was a transformation, a shaping, a foundation, and it's still ongoing today. Every drop in your glass contains atoms older than Earth itself. Hydrogen forged in the Big Bang. Oxygen born in dying stars. These elements came together, not once, but over and over, in space, in stone, in seas. And here they are, on your tongue, in your blood. In the tears we shed, in the rain that feeds the forests, the water we know is ancient, restless, and utterly irreplaceable. And as we trace its origins, we see not just how water came to Earth, but how through water, Earth became itself. When Earth's surface finally cooled enough to cradle oceans, the presence of water didn't simply mark a new phase in the planet's evolution. It rewrote the rules of what a planet could be. This wasn't just the appearance of a new chemical. It was the onset of a cascade. Water, so seemingly simple, became a catalyst for change, so sweeping, it touched every part of the Earth, from the crust below to the skies above. It didn't just fill basins. It began to sculpt continents, regulate climate, and alter the planet's chemistry in irreversible ways. To begin, we must return to the crust. Earth's surface shell, fractured, and floating on the hot, pliable mantle below. With the arrival of water, this crust underwent a subtle, profound weakening. Here's why that matters. Water acts like a lubricant in geological systems. It reduces the melting point of rocks. It infiltrates faults. It slips between mineral grains and makes them more mobile. When subducted into the mantle, it causes rocks to melt more readily, fueling volcanism. In short, water made tectonics possible. Not just plate tectonics as we understand it today, but the very capacity for the Earth's surface to shift, recycle, and renew. Without water, Earth's lithosphere might have remained rigid, static, like the surfaces of Mercury or the Moon. Instead, it cracked into mobile plates. These plates began to move, colliding, pulling apart, and sliding past one another, creating mountain ranges, ocean trenches, and island arcs. This movement gave the Earth its dynamic geology, and it continues to this day. Earthquakes, volcanoes, rifting valleys, all these owe something to water's subtle influence deep below. But the consequences didn't end with the crust. As the oceans deepened, they became vast chemical laboratories. Rainwater, slightly acidic from dissolved gases, began to erode the early land masses. This process, called weathering, broke down rock into sediments and released minerals into the sea. The runoff fed the oceans with calcium, magnesium, sodium, potassium, the elemental flavors that still define seawater today. Over millions of years, these reactions drew carbon dioxide out of the atmosphere, locking it away in carbonate rocks and cooling the planet in the process. This is the beginning of Earth's long carbon cycle, a planetary thermostat. Water wasn't just sculpting the surface, it was writing the climate. At the same time, the seas grew rich in dissolved iron, a result of the lack of free oxygen. This set the stage for one of Earth's most dramatic transformations, the oxygenation of the atmosphere. We touched on this before, the work of cyanobacteria and their photosynthetic ways. But here's where the chain reaction truly begins. Cyanobacteria, living in the shallow edges of ancient oceans, began producing oxygen. At first, this oxygen didn't accumulate in the air. It reacted with iron in the water, forming iron oxide, rust, which sank and layered onto the seafloor. These deposits would become the banded iron formations that modern geologists mine and study. Only after the iron was saturated did oxygen begin to gather in the oceans and finally in the atmosphere. This slow rise of oxygen, the Great Oxidation Event, transformed the biosphere. Oxygen is reactive. It breaks bonds. It fuels combustion and metabolism. When it first appeared in significant amounts, it was toxic to most of the life that existed. Whole microbial communities were wiped out. Extinction by oxidation. But for others, for organisms that could adapt or evolve, oxygen offered something new: energy. Vast amounts of it. Aerobic respiration, which uses oxygen to unlock energy from food, is far more efficient than anaerobic methods. It allowed life to become more complex, more active, more ambitious. This, too, was a water-driven change. Without oceans, there would have been no place for cyanobacteria to thrive. Without water, there would have been no medium for oxygen to dissolve, spread, and react. So, water created the stage, and life took its cue. Meanwhile, back at the surface, water continued its quiet work, cracking rocks, smoothing landscapes, moving sediments. Glaciers formed in higher latitudes and elevations, carving valleys and grinding mountains into silt. Rivers wove through the land like silver veins, creating deltas and floodplains rich in nutrients. The hydrological cycle, the endless loop of evaporation, condensation, and precipitation, became one of Earth's dominant engines. Powered by solar energy, it redistributed heat, shaped climate zones, and delivered fresh water to the continents. And with this came something else: habitability. Not just in the sense of survivable conditions, but in the profound sense that ecosystems could take root, spread, and diversify. Tidal pools, riverbanks, wetlands, each became a crucible for life to experiment with new forms, new strategies. Water enabled evolution to flourish. There's also the curious case of pH, the balance of acidity and alkalinity in Earth's waters. Early oceans were likely more acidic than today due to high levels of dissolved CO2. Over time, weathering of silicate rocks helped to neutralize this acidity, pushing the oceans toward a more balanced pH, one more favorable to life. Again, water was both agent and arena. It dissolved the minerals, carried the ions, buffered the changes. Then there are the salts. Why is seawater salty? Because rainwater erodes rocks. It picks up ions, sodium, chloride, calcium sulfate, and carries them into the sea. There, some are used by organisms. Others remain dissolved, accumulating over eons. The ocean, you might say, is a giant memory pool of the Earth's erosion. But this memory is not passive. Every ion in seawater influences its chemistry. The saltiness lowers the freezing point. The minerals affect buoyancy. The balance of nutrients determines what can grow. This too shapes life. Because as life evolved, it adapted not to generic water, but to the specific blend of Earth's oceans, the temperature, the salinity, the mineral content. In a very real way, life on Earth is not just water-based, it is earth-water-based. And still, the chain reaction continues. Water creates clouds. Clouds scatter sunlight. Scattered light cools the surface. Rain falls. Rivers flow. Sediments bury carbon. Subduction returns water and carbon to the mantle. Volcanism releases it again. This is endless cycling partnership between water and rock, water and air, water and life defines our planet. It is not a simple chain. It is a spiral, a self-sustaining dance. And water is the rhythm that drives it all. We've traced the threads of how water sparked tectonics, sculpted the crust, and powered the first stirrings of life. It's time to examine how it wove itself into the deeper choreography of the planet. Not as a background detail, but as the main tempo of Earth's rhythms. One of the most profound effects water had was on temperature. Not just the immediate climate of the early Earth, but the long sweeping arcs of geological time. Water by its nature resists change. It warms slowly, cools slowly, and moves heat across great distances. This thermal inertia became one of Earth's greatest allies. Let's take a moment to picture the early planet again. Volcanoes heave and spit along newborn ridges. The sun is younger, fainter, about 70% as bright as today. With less solar output, Earth should have been frozen, the snowball, from the start. But it wasn't. We know from ancient zircon crystals and isotopic studies that liquid water existed at least 4.3 billion years ago. This contradiction, a faint young sun and warm early oceans, puzzled scientists for decades. It's called the faint young sun paradox. And once again, water is at the heart of the answer. Carbon dioxide, methane, and other greenhouse gases likely outgassed from the mantle, created a thick, heat-trapping atmosphere. Water vapor, a powerful greenhouse gas itself, amplified the warming. The result, a planet that stayed just warm enough for oceans to remain liquid, even under a dim sun. But this balancing act was fragile. Too much greenhouse gas, and Earth would have tipped toward a Venusian fate. An inferno. Too little, and it would have frozen solid like Mars. The key difference, water didn't just participate in the climate, it regulated it. Here's how. When Earth got too warm, chemical weathering of silicate rocks accelerated. This process draws CO2 out of the atmosphere, locking it into carbonate minerals. It's slow, but incredibly effective over geological timescales. When Earth cooled, weathering slowed. CO2 built up again through volcanic outgassing, and temperatures rose. This long feedback loop, mediated almost entirely by water and rock, acted like a planetary thermostat. It kept the planet in the Goldilocks zone, not too hot, not too cold, for billions of years. And then, occasionally, it broke. There were times in Earth's history when water, instead of maintaining balance, tipped it into chaos. One such time was the Snowball Earth events, deep freezes that occurred roughly 700 million years ago. During these periods, glaciers may have extended to the equator. Oceans froze over. The planet became a glistening white marble, reflecting sunlight back into space and deepening the chill. What triggered these freezes is still debated. One theory suggests that continents clustered near the equator increased weathering and drew down CO2 too rapidly. With less greenhouse gas, the planet cooled. Ice spread, and once it reached the tropics, the albedo effect took over. White ice reflecting more sunlight, creating a feedback loop of freezing. But here's where water's duality shines. As volcanic activity continued under the ice, CO2 levels crept upward. With no open oceans to absorb it, CO2 built up in the atmosphere, eventually triggering a greenhouse rebound. When the ice finally melted, it did so catastrophically. Massive floods, runaway warming, weathering restarted, CO2 fell, balance returned. These dramatic swings weren't interruptions in Earth's story. They were part of its rhythm, extreme verses in a song conducted by water. Each time Earth froze or baked, life had to adapt. Some died, others diversified, and in the aftermath, evolution surged. After Snowball Earth came the Eddy period, a strange and fertile time when multicellular life blossomed in new ways. Some scientists believe the trauma of global freezing, followed by a rapid thaw, may have pushed evolution forward, opening new ecological niches. This pattern, catastrophe followed by creativity, is deeply etched into the fossil record, and water is always the medium. Consider mass extinctions. The Empyrean event, the worst extinction in Earth's history, wiped out over 90% of marine species. It's thought to have been triggered by massive volcanism in Siberia, which pumped greenhouse gases into the air and acidified the oceans. Water again was both the victim and the vector, absorbing CO2, warming, losing oxygen. Life suffocated in its own medium. But afterward, ecosystems recovered, new species arose, coral reefs returned, and life continued, finding new forms in old waters. Even on a daily scale, water shapes biology. Circadian rhythms in plants and animals follow cycles of evaporation and moisture. Migration routes trace river paths. Reproduction, hibernation, feeding, all tuned to the rhythms of water. The hydrosphere doesn't just support life, it conducts it. And now we must zoom out one step further to realize a larger truth. Water did not merely transform Earth, it differentiated Earth. Because of water, Earth became the only planet in the solar system with visible tectonic plates, a carbon cycle, long-lived volcanism, and life. Not because water was present, but because it was persistent, because it cycled deep and slow, because it carved the world and cooled its fire. Other planets had water briefly. Mars had rivers, lakes, perhaps seas. Venus may have once had oceans, but only Earth held on to it, buffered it, buried it, breathed it. That's why, when we search for life elsewhere on exoplanets orbiting distant stars, the first thing we look for is water. Not as a guarantee, but as a hint. Because water isn't a luxury. It's a lens. It shows us which planets might work, which ones can balance chaos with calm, which ones might carry their own spirals of chemistry and change. In this way, Earth's oceans are more than a feature. They are a fingerprint, a symbol of deep stability in the face of cosmic violence, a sign that amidst the cold and the dark, a world can hold warmth and keep it. And so, the chain reaction continues. Water falling, rising, cycling, carving valleys, powering storms, carrying whispers of ancient stars. It began with impacts and dust. It led to rivers and rain. And still it flows. To grasp the full measure of Earth's water story, the delicate interests of collisions, chemistry, and deep planetary cycles, we must now step even further back beyond the Earth, beyond the solar system. Because while our oceans feel uniquely ours, personal even, their origins reach into the deep past of the cosmos, past planets, past stars, into the cold, dark clouds from which everything we know once swirled and gathered. Let's begin with a simple, astonishing truth. The water you drink today is older than the sun. This isn't poetry, it's chemistry. The hydrogen in water, that light, buoyant element, was born in the first few minutes after the Big Bang. In that brief, incandescent infancy of the universe, as the first protons cooled enough to form atomic nuclei, hydrogen emerged. Some of that hydrogen went on to fuel stars. Some joined with oxygen in the right conditions to become water. The oldest water we have ever detected, found in distant interstellar clouds, is over 12 billion years old. These clouds drift through galaxies, cold and quiet. Some condense into stars. Some collapse into planetary systems. And embedded in these clouds are icy grains, water locked onto dust, drifting in the vacuum of space for eons. When our solar system was just beginning, when the sun was still forming from a collapsing nebula, some of these icy grains were there. They weren't made in our solar system. They were inherited, and they survived not as puddles, not even as ice cubes, but as frost clinging to tiny specks of dust. These specks would eventually be drawn into the solar disk, the flat, rotating plane of matter from which planets grew. In the colder regions of this disk, far from the sun, water ice was common. Closer in, it was too hot. Only rock and metal could survive. But gravity and turbulence don't follow neat boundaries. Material migrates. Inner regions can receive deliveries from far afield. That's likely how Earth got its water-bearing rocks, from this radial mixing of warm and cold, dry and wet. Some scientists suggest that up to 50% of Earth's water predates the solar system. That means that the molecules filling your coffee mug this morning were born not on Earth, not even near Earth, but in the dark between stars. That's the broader context. Water didn't appear when Earth was born. It was waiting. But Earth is not the only world touched by water's hand. As we've mentioned, Mars once had lakes and rivers. We see the dried-up deltas, the braided channels, the ancient lake beds. Rovers have found clays and minerals that only form in the presence of water. There may still be briny aquifers deep underground. Venus, Earth's twin in size, but opposite in temperament, may once have had oceans, but its proximity to the sun doomed it. The oceans evaporated. UV radiation split the water. Hydrogen escaped to space. Oxygen bonded with rocks, or escaped as well. What's left is a scorching world with barely a trace of its wet past. Even moons in the outer solar system echo Earth's wetness. Europa, one of Jupiter's moons, is covered in ice. Beneath it, a subsurface ocean warmed by tidal forces from Jupiter's gravity. Ganymede and Callisto may also hide oceans. So does Saturn's Enceladus, a tiny, brilliant moon that shoots geysers of salty water into space. Titan, another of Saturn's moons, has lakes and rivers, not of water, but of methane, a chemical mimicry of Earth's hydrological cycle playing out in hydrocarbons at 179 degrees Celsius. And beyond our solar system, we found exoplanets in their stars' habitable zones. Some may be ocean worlds covered entirely in water, with no land at all. Others may be desert planets or ice-covered orbs. We don't yet know, but we keep searching, because if there's one lesson from Earth's watery saga, it's this: water changes everything. It's not merely a solvent, it's a setting, a sculptor, a seedbed for chemistry, and perhaps, inevitably, for life. Which brings us to another deep truth. Earth's water isn't just old, it's linked. The hydrogen atoms in your body may have once circled a comet in the Kuiper Belt, or been forged in a long-dead star. The oxygen in your lungs may have been part of a glacier in the last ice age, or drifted as vapor through the breath of the first forest. All water on Earth is part of a single planetary system. It evaporates, it condenses, it falls, it freezes, it flows, but it never leaves. Not in significant amounts. Not anymore. That means the water inside you right now may once have filled a dinosaur's footprint, or carved a canyon in Pangaea, or trickled through the roots of a plant 400 million years ago. Water connects moments. Water connects beings. It is a shared inheritance not just across space, but across time. And this inheritance carries with it a remarkable pattern. Every major transition in Earth's history, from molten fireball to blue ocean world, from microbial mat to rainforest, from extinction to evolution, has been accompanied or even enabled by water. Not just as a chemical, but as a force. It cools, it erodes, it carries, it dissolves, it buffers. It is quite literally the medium through which change flows. That's why paleoclimatologists study ice cores to read the story of ancient climates. Why astrobiologists look for water signatures on alien worlds. Why geologists trace ancient shorelines and riverids to map the slow ballet of the continents. Because in the end, to understand Earth is to follow the water. And to follow the water is to see not a static planet, but a living, breathing one. One whose heart pulses not just with magma and rock, but with tides, clouds, and rivers. So when we ask, where did Earth's water come from? We're really asking something deeper. We're asking how the universe learns to hold warmth, how stardust becomes rivers, how chaos gives rise to calm, and most of all, how a pale blue dot learned to sing its soft liquid song in the dark. In the quiet halls of laboratories, on windswept outcrops in Antarctica, and among the fragments of space rocks tucked in museum drawers, a chorus of human curiosity has echoed for centuries. The question, where did Earth's water come from? Might sound like mythology, but it's been treated with the rigor of chemistry, the patience of geology, and the daring of cosmic imagination. Let's begin with a name, not shouted from textbooks, but whispered reverently in research circles. John Valley. In the early 2000s, Valley, a geochemist from the University of Wisconsin-Madison, examined tiny crystals known as zircons, minerals that can survive immense heat and pressure, preserving a record of Earth's earliest days. These zircons, plucked from ancient rocks in the Jack Hills of Western Australia, were over 4.44 billion years old, and inside them, a subtle signal. Isotopic signatures of oxygen that suggested interaction with liquid water. It was astonishing. These were not ocean pebbles. They were time machines, showing that Earth had stable crust and possibly surface water a mere 100 million years after its formation. Before this, scientists had assumed that the Hadean Earth, named after Hades, was entirely molten, dry, and chaotic for hundreds of millions of years. But these zircons hinted otherwise. They spoke of rain, of oceans, of a quieter world sooner than expected. John Valley didn't claim to have found the first drop of water, but he helped shift the story's timeline backward into a more ancient, more hydrated past. But the puzzle didn't end there. Around the same time, researchers were analyzing meteorites, not just for metals or shock scars, but for water. Enter Alexander Halliday and his team at Oxford. Using isotopic techniques, Halliday's group began comparing the DH ratios, remember, deuterium to hydrogen, of different solar system materials. They focused especially on carbonatous chondrites, those ancient water-rich meteorites that seemed to whisper Earth's name. The results were striking. The hydrogen in these meteorites matched Earth's oceans more closely than any comet ever had. It was a quiet revolution. For decades, comets had been the darlings of the water origin theory. Beautiful, dramatic, easy to imagine crashing into a dry Earth and releasing their icy burdens. But Halliday and others showed that the chemistry didn't line up. Comets, especially those from the cloud, had far too much deuterium. The match was off. The water must have come from something else, something quieter, stonier, closer. It was a moment of scientific humility, a reminder that the most spectacular explanation isn't always the right one. Meanwhile, in laboratories like those of Lydia Hallis at the University of Glasgow, the tools grew more precise. Hallis and her team studied olivine inclusions from volcanic rocks in Hawaii, remnants of the deep mantle brought to the surface. Inside, they found hydrogen with isotopic ratios lower than those in the oceans, even lower than those in chondrites. It was an unexpected clue. Could this mean some of Earth's water, or at least its hydrogen, came not from asteroids at all, but from the solar nebula itself? It was a bold suggestion. If true, it would mean Earth captured hydrogen gas directly from the dust of materials surrounding the young sun, incorporating it into its mantle during formation. Later, that hydrogen could have reacted with oxygen-bearing minerals to form water. Not all scientists agree. The debate is still active. Butt's findings reopened an old possibility that Earth's water wasn't entirely delivered. Some of it may have been retained. The search has also gone skyward. Missions like ES's Rosetta, which studied Comet 67P Churyumov-Gerasimenko, provided a wealth of data on cometary composition. When Rosetta analyzed the comet's ditch ratio, it found a value 3 times higher than Earth's. It was another nail in the coffin of the comets brought the oceans theory. And yet, every finding added nuance. Some comets, particularly Jupiter family ones, have lower DH ratios. Some are closer matches, but as a group, they're inconsistent. This is the beauty of science, especially planetary science. It's not a tale of consensus. It's a tale of convergence. Dozens of teams, using dozens of methods, studying everything from Martian meteorites to lunar basalts, began building a picture that Earth's water is not from one source. It is from many. Some from asteroids, some from the mantle, some perhaps from interstellar ice that predated Earth entirely. Each study adds a brushstroke, Each result, even when it contradicts the last, helps refine the truth. And beyond the labs, the fieldwork continues. In Antarctica, meteorite hunters walk the frozen plains with snowmobiles and tongs, collecting space rocks that have lain undisturbed for thousands of years. In Japan, scientists study asteroid samples returned by Hayabusa 2. Tiny grains from Ryugu, offering the first direct samples of a carbon-rich asteroid. Every particle holds a clue. Because when it comes to Earth's water, the story isn't just told by oceans. It's told by isotopes, by minerals, by the ghosts of impacts frozen in rock. And it's told by the people, the geochemists, planetary scientists, cosmochemists, who dedicate their lives to decoding the whispers of hydrogen and oxygen. They are translators, really taking the ancient language of atoms and rendering it into human wonder. And perhaps that's the most beautiful part of the discovery process. Not just the findings, but the minds that found them. We live in a world where stories are often told in words, but the story of Earth's water, of its presence, persistence, and profound consequence, is written in minerals, isotopes, and silent equations. It's a tale assembled not by poets or prophets, but by a lineage of patient thinkers, armed with lasers, mass spectrometers, and a near-religious devotion to precision. Among them is Meenakshi Wadhwa, a planetary scientist whose work bridges cosmic chemistry and astrobiology. Her studies of hydrogen isotopes and meteorites helped clarify how water was distributed in the early solar system. Wadhwa's research added momentum to this idea that water-bearing asteroids, not icy comets, were the more likely deliverers of Earth's oceans. In an interview, she once likened her work to archaeology, except on a planetary scale. Every meteorite is a messenger, she said. Each one carries a story from a time before Earth even existed. This sentiment echoes throughout the discipline, because planetary science isn't just about rocks. It's about context, connection, continuity. You see, the idea that we can look at a pebble that fell from the sky and read it like a chapter of an ancient book. This isn't fantasy. This is lab work. And to read that book, scientists have developed tools of astonishing delicacy. Take the secondary ion mass spectrometer, or SIMS. With it, researchers can vaporize minuscule spots on a sample and analyze the isotopes within. These instruments can measure the pH ratio of individual grains of olivine, or pyroxene. They can distinguish between water locked in a mineral lattice and water added later by weathering. With tools like SIMS and the more recent atom probe tomography, scientists don't just study rocks, they interrogate atoms. And these interrogations have taken us to the moon. Yes, the moon, long assumed to be dry and barren. But in the 2000s, that belief was overturned. NASA's Moon Mineralogy Mapper aboard India's Chandrayaan-1 mission detected spectral signatures of hydroxyl, the O group that hints at water on the lunar surface. Follow-up missions confirmed it. The moon had water, not pools or oceans, but ice trapped in permanently shadowed craters and hydroxyl bound in minerals. Then came a bigger surprise. Some lunar volcanic glass beads, returned by Apollo astronauts, contained measurable amounts of water. Again, isotopically analyzed in labs decades later. These beads, formed from magma, suggested that water existed in the moon's interior at the time of its formation, which raised a bold question. If the moon formed from Earth's own mantle in the aftermath of the Theia impact has water, then Earth's interior must have had it too. It was a clue, not just about the moon, but about Earth's earliest days. A silent echo of a shared history. These kinds of insights, drawn from space missions, meteorite labs, and quantum instruments, highlight how interdisciplinary the hunt for Earth's water truly is. It involves astrophysicists who model the collapse of interstellar clouds. It involves chemists who measure the exact vibrational frequencies of water molecules under pressure. It involves planetary geologists who read craters, sediment layers, and tectonic scars like hieroglyphs. It involves computational scientists running simulations of planet formation, modeling whether and how volatiles like water can survive the furnace of accretion. And it involves engineers, hundreds of them, designing spacecraft that can survive launch, navigate millions of kilometers, and bring back a dust grain the size of a sesame seed, a grain that might tell us how Earth got wet. The OSIRIS-REx mission, for instance, returned samples from asteroid Bennu, a carbonaceous body suspected to be rich in hydrated minerals. Launched in 2016, it reached Bennu, mapped its surface with breathtaking resolution, scooped up regolith, and returned to Earth in 2023. That handful of asteroid dust is now being analyzed in labs around the world. Already, preliminary results show the presence of phylloseic, clay-like minerals that form in the presence of water. Once again, the cosmic breadcrumb trail leads back to hydration. And then there's Japan's Hayabusa 2 mission, which brought back samples from asteroid Ryugu in 2020. Among its findings, organic molecules and hydrated minerals. The story repeats over and over. Water, water, water. What's remarkable isn't just the data, it's the persistence. Because this isn't fast work. A single analysis might take years. A hypothesis might wait decades for confirmation. Some of the meteorites being studied today were collected in the 1960s. Some data was locked in them, waiting for instruments that hadn't yet been invented. Science here is not a sprint. It's a pilgrimage. And these pilgrims, these geochemists and astronomers, these spectroscopists and modelers, are part of a chain that stretches back further than you might think. In the 18th century, German chemist Henry Candish was the first to show that water wasn't an element, but a compound made of hydrogen and oxygen. In the centuries that followed, as the periodic table emerged, as atomic theory solidified, water became a lens through which to explore not just chemistry, but the cosmos. Each advance in understanding water, its structure, its phase changes, its ability to dissolve and transport, made it easier to recognize its fingerprints in the wild. So, when we look at Earth and ask, where did all this water come from? We're also asking, how do we know anything about something so ancient? And the answer is always human ingenuity. It's in the field teams chipping meteorites from Antarctic ice. It's in the doctoral students running isotope samples late into the night. It's in the mission planners who chart a course to a tumbling asteroid millions of miles away. It's in the grant writers, the data analysts, the journal editors, the system, the scaffolding of inquiry. Every drop of understanding we've gained about Earth's water came from a drop of someone's effort multiplied over decades. And yet, even with all this effort, we still don't know everything. Some scientists still argue for a nebula origin. That hydrogen from the solar nebula played a larger role than we think. Others explore the implications of water's strange properties, its anomalous expansion upon freezing, its high surface tension, its ability to mediate the chemistry of life. Some pursue the question of how water influenced plate tectonics, or whether deep mantle reservoirs cycle water on billion-year scales. It's not a closed case. It's an ongoing mystery. But it's a mystery we're solving together, across borders, across disciplines, across decades. Not with shouts, but with whispers. The soft clink of a sample tube, the silent hum of a laser, the slow, steady patience of minds that know the ocean began with a question. Beneath every ocean wave, behind every raindrop on a window pane, and within every tear ever shed, lies a molecular dance as ancient as the stars. If water is the storyteller of Earth's past, then its script is written not in ink, but in isotopes. The quiet signatures that whisper truths too subtle for the naked eye. And to hear those whispers, science must dive deep. Let's start with geochemistry, the discipline that more than any other has taught us to see the world through elemental eyes. Geochemists are alchemists of the real. They take rock, ice, gas, and water, and reduce them to ratios. The DH ratio, the ratio of deuterium to hydrogen, has already played a central role in our story. But why is this ratio so powerful? Because deuterium is rare. For every 6,000 atoms of regular hydrogen, there's roughly one deuterium. Yet in different parts of the cosmos, and in different types of materials, that ratio changes. It becomes a chemical passport, a timestamp, a clue. Water formed in the interstellar medium, for instance, has a higher DH ratio due to the extreme cold. In contrast, water formed from solar nebular gases tends to have much less deuterium. So when scientists study the DH ratio in ocean water, in meteorites, in lunar glass, or in cometary ice, they are building a map, not of places, but of origins. In the lab, this measurement requires extraordinary precision. Enter the mass spectrometer, a machine capable of separating atoms by their mass and charge. Some are so sensitive they can detect variations in isotopic ratios to parts per million. A drop of water, vaporized and fed into the machine, becomes a stream of data. Each peak on the graph tells a piece of the story. Mass spectrometry has allowed scientists to trace the isotopic evolution of Earth's water over time, revealing that the ocean's DH ratio has remained surprisingly stable for billions of years. That consistency suggests a well-mixed reservoir supported by the global water cycle and possibly buffered by deep Earth reservoirs. But to look deeper, not just at surface chemistry, but at planetary dynamics, we turn to geophysics. One of the most surprising revelations of recent decades is the existence of deep mantle water, not as pools, but as molecules locked within the crystalline structure of minerals like wadsleyite and ringwoodite. These minerals exist only at high pressures, hundreds of kilometers below Earth's surface, and yet they can store vast amounts of water, up to 1% of their weight. When scaled to the volume of the mantle transition zone, that translates to potentially as much water as all the surface oceans combined. We know this because of lab experiments in diamond anvil cells, instruments that crush tiny samples under extreme conditions. Samples between two diamonds, replicating the pressures of the deep mantle. When researchers synthesize wadsleyite or ringwoodite and add water, they find these minerals eagerly absorb it into their structure. And in 2014, a real-world confirmation arrived. A team led by Graham Pearson discovered a microscopic inclusion of ringwoodite inside a diamond from Brazil. The inclusion contained water, not liquid, but structurally bound. It was the first direct evidence that the mantle transition zone is not dry. This single inclusion was like finding a drop of dew in a cave and realizing the whole cavern may be wet. Now, let's look up. To understand how planets acquire water in the first place, we turn to astrophysics and cosmo. In protoplanetary disks, the flattened, swirling clouds of dust and gas that orbit newborn stars, water exists in multiple forms. Vapor dominates the inner regions. Ice coats grains in the outer zones. The boundary between them is called the snow line, where temperatures drop low enough for water to freeze. Planetary formation is shaped by this snow line. Inside it, rocky planets like Earth form, hot, dry, and dense. Beyond it, gas giants and icy bodies take shape. Jupiter, Saturn, Uranus, Neptune, and a myriad of comets and Kuiper Belt objects. But material doesn't stay put. Turbulence, migration, and gravitational nudges cause mixing. Astrophysical models now simulate how icy planetesimals from beyond the snow line can be scattered inward, colliding with the forming Earth and delivering water. One model, known as the Grand Tack, suggests that Jupiter may have migrated inward early in the solar system's history, scattering water-rich asteroids toward Earth, then moved outward again, like a ship tacking in the wind. This early planetary ballet could explain the delivery of volatiles to the inner solar system. These models aren't guesses. They're coded into vast simulations run on supercomputers, parameterized with observed data, and tested against the isotopic and dynamical makeup of the solar system. Even the composition of exoplanets, planets beyond our solar system, is helping refine these ideas. When we detect water vapor in the atmospheres of hot Jupiters, or measure the density of super-Earths and suspect they may be ocean worlds, we're learning how common or rare Earth's water story might be. And what about the chemistry of life itself? Biochemists study how water's unique properties enable life. Its polarity, its ability to dissolve salts and proteins, its high heat capacity, its strange expansion when it freezes. All these quirks make water not just useful, but essential. Some researchers even propose that water's oddities are not accidental, but necessary preconditions for life anywhere in the universe. In this view, the emergence of life is not merely the result of carbon and time, but of water's specific capabilities. No other solvent, they argue, has quite the same balance of reactivity, stability, and versatility. Which brings us to the final frontier of this science: time. Radiometric dating based on the decay of isotopes like uranium to lead or potassium to argon lets us pin dates on rocks from meteorites to moon samples to Earth's oldest zircons. Using these clocks, scientists have built a timeline. Earth formed about 4.54 billion years ago. Zircons suggest stable crust and water interaction by 4.4 billion years ago. Carbon-rise sediments appear by 3.8 billion. Life by at least 3.5 billion. And through it all, water, not as a newcomer, but as a participant. The deep science shows us this. Earth's water was not an afterthought. It was present during accretion. It shaped differentiation. It influenced climate, and it set the stage for biology. It is not a footnote. It is the through line, the narrative thread that stitches the Earth together, from magma to mountain to microbe. And the more we study it, the more we realize it's not just about where water came from. It's about what water made possible. From the moment liquid water pulled on the young Earth's cooling crust, It began its long and quiet work, the shaping of life, the scripting of change. But water did not rush this task. It moved with patience, carving valleys over millennia, buffering climates over eons, and offering its embrace to the first fragile flickers of life. And when life did emerge, water was not just present, it was essential. In those early oceans, acidic, warm, stirred by hydrothermal vents, chemistry came alive. Here in the rich mineral plumes rising from the seafloor, molecules found the energy and the structure to replicate. Amino acids assembled. RNA strands formed. Simple lipid bubbles became primitive cells. The origin of life may never be fully known, but nearly every serious hypothesis places it in or near water. Why? Because water allows movement. It enables molecules to drift, collide, react. It dissolves nutrients. It facilitates the folding of proteins and the flow of ions. It is both medium and message. And in those first billion years, life remained microscopic, single-celled, soft-bodied, drifting in the currents. But over time, water began to host more than chemistry. It became a nursery of complexity. Photosynthetic microbes, like cyanobacteria, began exhaling oxygen. Slowly, this gas accumulated first in oceans, then in the air. The Great Oxidation Event was not an explosion, but a shift, gradual but irreversible. Oxygen poisoned many of Earth's original anaerobic inhabitants. Extinction swept across the microbial world. But oxygen also enabled new forms of metabolism, new possibilities. The biosphere, once limited to anaerobic life, clinging to hydrothermal vents or fermenting sugars in the dark, began to expand. Oxygen allowed for larger cells, the eukaryotic cells with nuclei, organelles, internal complexity. From these, multicellular life would one day rise. But first, there were more setbacks. The Proterozoic eon, from 2.5 billion to 541 million years ago, was long and strange. Sometimes called the boring billion, it was anything but. Life diversified quietly. Complex cells appeared. Ecosystems evolved in subtle ways. Yet to the naked eye, little changed, and beneath it all, the water cycled. Continents drifted. Oceans opened and closed. Tectonic plates collided and pulled apart. Sediments accumulated, bearing the chemical traces of changing life. Then, around 720 million years ago, Earth froze. Glaciations spread across the globe, possibly reaching the equator. Twice, in fact, during the cryogenian period, Earth may have become a snowball. Oceans sealed under ice. Photosynthesis halted. Most life likely retreated to geothermal refuse near hydrothermal vents or in meltwater pockets beneath glaciers. It was one of life's greatest tests. And water, paradoxically, both threatened and saved it. Because beneath the ice, liquid water remained, and when the glaciers melted, they released nutrients into the oceans, fueling explosive blooms of algae and microbes. Oxygen surged. Life rebounded. The Cambrian explosion followed. About 541 million years ago, a riot of animal life burst into being. Trilobites, worms, early vertebrates, shells, and skeletons appeared. Predation evolved. For the first time, the fossil record truly opened, revealing the strange, beautiful inventiveness of life. This diversification happened in water. Marine ecosystems became the stage for evolution's most daring experiments. Filter feeders, swimmers, burrs, Coral reefs, schools of fish, cephalopods with inquisitive eyes, jellyfish pulsing in the currents. The land, still barren, waited its turn. And when life finally came ashore, first with mosses and liverworts, then insects and amphibians, it carried water with it in every cell, in every breath. Even today, every terrestrial organism is at heart aquatic. We carry the chemistry of the ocean in our blood, in our sweat, in our tears. Water was the womb we never left. But the Earth's history is not linear. It loops and breaks and begins again. Mass extinctions swept the planet 5 times in total. The Permian 252 million years ago saw over 90% of marine species vanish, possibly triggered by massive volcanic eruptions in Siberia. It turned oceans acidic and anoxic, deprived of oxygen. Water again became inhospitable. And then it recovered. Fish returned. Coral reefs rebuilt. The sea gave rise to the ancestors of dinosaurs, birds, mammals. Each time life was knocked back, it regrew in the water first after the Cretaceous extinction 66 million years ago, when an asteroid struck Earth and ended the reign of the dinosaurs. The oceans offered refuge once more. Tiny plankton, the base of the marine food chain, bounced back quickly. Marine ecosystems healed. Whales and dolphins would one day rise. Coral reefs blossomed. And eventually, humans appeared, building boats, drawing maps, chasing fish, and peering into tide pools with questions older than language. Through all this, water persisted. It didn't just support life, it adapted with it. Seawater composition changed. Salinity fluctuated. Ocean currents shifted with the continents. Ice ages came and went. Sea levels rose and fell. Each shift redrew coastlines, built new habitats, triggered migrations. Even today, the thermohaline circulation, the global conveyor belt of ocean currents, regulates Earth's climate. Warm water moves from the equator to the poles, cools, sinks, and returns. This massive loop distributes heat, influences rainfall, and feeds ecosystems with upwelling nutrients. Without it, monsoons would fail, forests would wither, fisheries would collapse, and fresh water, that precious fraction of Earth's total water, carved its own legacy. Glaciers sculpted valleys and formed lakes. Rivers became highways of civilization. Aquifers stored rain for millennia. From ancient wells to modern desalination plants, humanity has sought, revered, and fought over fresh water. We are, as Leonardo da Vinci once wrote, water's conduit. It moves through us. We divert it, bottle it, waste it, pray for it, and still it flows. Even now, water remains the thread holding Earth's surface in balance. It stabilizes climate, moderates heat, reflects sunlight from snow, absorbs carbon in rain, carries sediment, nutrients, and seeds. And underground, in the mantle, water still cycles, subducted in slabs returned in lava, maintaining the deep balance of our planet's interior. It's easy to forget that. We think of oceans as eternal, rivers as granted, rainfall as inevitable. But every drop has a history. Every molecule was forged in stars, wandered through space, arrived by stone or steam, and became part of Earth's vast, slow breath. And in that breath, life has flourished, faltered, and returned again. Always accompanied, always embraced, always shaped by water. So the next time you sip from a glass or listen to rain on a rooftop, remember, this is not just liquid, it's legacy. It's Earth whispering its oldest story. Look around you now. The sky might be overcast or electric blue. The ground may be soaked, frozen, or dry as dust. But somewhere above, beneath, within, water is moving quietly, relentlessly. A mist, a trickle, a pulse. Earth is breathing, and that breath is wet. And we, you, me, all of us, are part of that movement. We often forget that. We talk about water as if it's other, as if it's a commodity to be managed or extracted. But in truth, it is a mirror. When we study water's journey, we are studying our own. Because every drop of water on Earth, ancient, restless, immortal, tells the story not just of planetary formation, but of what it means to be alive here now, in this fragile moment. It's strange to think how recent our understanding of water's role truly is. Just a few centuries ago, we thought water was one of the classical elements, unchanging, indivisible. We didn't know it had a molecular structure. We didn't know it had memory, not in a mystical sense, but in a scientific one, the kind that lingers in isotopes and sediments, in glacial layers and salt flats. Today, we map aquifers with satellites. We sample comet tails with spacecraft. We can watch a droplet form in slow motion and see the physics of surface tension unfolding like a dance. And still, for all our tools and models, water remains elusive in its implications. Because the story of water is not just geological or chemical, it's moral. We live in a time when climate change is no longer a theory. The ice is melting, the seas are rising, droughts deepen, floods grow fiercer, rivers run dry while cities grow thirsty. Water, once our inheritance, is becoming our responsibility. The very processes that made Earth habitable, that buffered its climate, cycled its carbon, regulated its temperature, are now being strained by our actions. We have altered the composition of the atmosphere. We have deforested the catchments. We have dammed and diverted and drained. And still, we rely on water to forgive us. We expect the rains to come, the snow to melt, the reservoirs to refill. But nature does not guarantee balance. It maintains it with feedback, with cycles, with consequence. And yet even here, there is hope. Because just as water created the conditions for life, so too can it inspire a kind of humility. A river teaches patience. An aquifer teaches foresight. A glacier teaches endurance. And when we protect water, when we restore wetlands, repair watersheds, reduce pollution, we are not just preserving a resource. We are participating in a story that began long before us and will, if we are wise, continue long after. That story stretches back to stardust and forward to sustainability. It links the hydrogen in your blood to the hydrogen in a comet's tail. That story stretches back to stardust and forward to sustainability. It links the hydrogen in your blood to the hydrogen in a comet's tail. That story stretches back to stardust and forward to sustainability. It links the hydrogen in your blood to the hydrogen in a comet's tail. It links the hydrogen in your blood to the hydrogen in a comet's tail. Connects the oxygen you breathe to the oxygen once released by ancient algae drifting in shallow seas. It reminds us that we are not separate from Earth's systems. We are systems within systems. Water within water, consciousness within chemistry. And if Earth's past has taught us anything, it's that resilience is real, but not inevitable. The planet has recovered from asteroid impacts, supervolcanoes, and mass extinctions. Life has clawed back from the brink again and again. But recovery takes time, millions of years, entire epochs. We don't have that kind of time. We are not the dinosaurs caught unawares by a falling sky. We are the first species to understand the sky, to track the CO2, to measure the ice, to model the currents. We are the first to witness Earth's water systems in real time, not as background, but as bellwethers. And we're a first to have a choice, to turn the tap gently, to plant a tree, to vote for the river, the reef, the rainfall, to remember that every bottle, every flush, every pipe is part of a cycle older than language. This is not about guilt, it's about perspective. Water came to Earth through violence, collisions, impacts, chaos. It became serene through balance, cycling, flowing, evolving. It became sacred through use, by slaking thirst, feeding fields, baptizing faiths, and now it waits, not for our praise, but for our partnership. Because we are not separate from the oceans. We are made of them, not symbolically, literally. Your tears, your sweat, your blood, you're all echoes of the same ancient molecule that fell from space, steamed from magma, cooled terrain, pulled in ponds, and birthed your ancestors. So let us honor that story, not with monuments or myths, but with care, with wiser policies, with fairer sharing, with cleaner industry and kinder choices. With the understanding that when we protect water, we protect the memory of starlight and the possibility of future dawns. So here we are, at the shoreline of a story older than mountains and deeper than time. We followed water from the cold edges of space to the hot belly of the Earth. We've watched it fall, rise, reshape, and return. We've seen it cradle life, challenge it, and carry it through fire and ice. And we've glimpsed how it still flows, quietly, holding together the pieces of this fragile, magnificent planet. And maybe now we can ask the question a little differently. Not just where did water come from, but what does it mean to belong to a world made of water? To know that your heartbeat, your breath, your thoughts, they're all stirred and sustained by the same ancient current that wore down continents and lifted whales. To realize that the cup in your hand contains echoes of comets, of clouds, of crocodiles, of poets. That nothing you touch, no fruit, no book, no bird, exists without water's quiet signature. And that in turn, you are part of that cycle. Not a bystander, not an observer, but a participant. So take care of the rain. Walk gently by the stream. Let your awe be active. Because wonder isn't just a feeling, is a decision, a way of seeing again and again, the miracle in the mundane. Thank you for joining me on this journey through Earth's most enduring element. If this story stirred something in you, a question, a memory, a ripple of wonder, feel free to share it in the comments below. I'd love to know what water means to you. And if you'd like to hear more stories like this, slow, deep, and full of quiet science, feel free to like, subscribe, and settle in with us next time. We've only just begun to trace the threads of Earth's ancient saga. Until then, stay curious, stay kind, and stay fluid. This has been Just About Earth, and I'll see you again downstream.